In section 5.1, we'll look at composite functions, how to evaluate them, find the domain of a composite function, break them apart, and see examples of real-world situations using composite functions. Precalculus Online starts now. In section 5.1, we'll look at composite functions. And let's get the definition of composite functions here. So the notation for composite functions looks like this. It's f, and then this little circle, g of x. And what this means is you take f of g of x. So everything's sort of relational here. Notice that the f here was the one that was mentioned first in the composition, and that function is the outside function. The g was the one on the right side here, and that's the inside function. So basically what composition of functions results in is you take one function and evaluate it inside of another function. So you're going to take the g function and you're going to put it inside the f function. Let's show some examples of this. Example 1, let f of x equal x squared plus 1 and g of x equal 3x plus 2. Find the following. A is f composed with g of 2. That literally means f of g of 2. So the first thing I'm going to evaluate is what is g of 2? Well, the g function is this 3x plus 2 function, so I'm going to plug 2 into that. I'm going to write it all out here. So it's going to be f of, and now I plug in the 2 into the g function. So 3 times 2 plus 2, that turns out to be 8, so we have f of 8. And now I take 8 and I plug it into the f function. The f function is x squared plus 1. So this becomes 8 squared plus 1, which is 65. So this composition results in 65. Let's take a look at the part B, g composed with f of negative 1. So now the g and the f are reversed, and so we have to take that into consideration here. This one is asking for g of f of negative 1. So first we evaluate negative 1 in the f function. So that's going to be g of negative 1 squared plus 1. Negative 1 squared is 1 plus 1 is 2, so this is asking for g of 2. And now we take 2 and plug it into the g function, and that's 3 times 2 plus 2, which is 8. So g composed with f of negative 1 is 8. And you can compose in any order. You can compose 3 functions, 4 functions, whatever. You compose a function with itself. You know, all sorts of things can happen here. But that's the basics behind doing composition of functions. You're taking one function and plugging it into another function. Now, something that can get a little complicated with composition of functions is the domain of the functions. So let's sort of break that apart, and I've got this set up here with the colors and everything. So the first part right here, this little section down here, this is going to be the domain of g. And the part that's the domain of g is this entire body here, this entire section here. And I've kind of split it off with the yellow and the green, and that'll make sense here in a second. Now, what happens if you take a value x in the domain of g and you apply the g function? Well, you end up with g of x. So that makes this section here the range of g. Recall that the domain of a function is the set of x values that you can use inside the function, and the range is the set of y values that you get out of the function. All right, now let's take this one step further here because we really want to get to the composition part. Let's go ahead and make this blue and little overlap section here. We're going to make this little part right here. This is going to be the domain of f. And the question is, what happens if I take a value from there? Well, if I take a value from there and I map it with the f function, you end up with f of x. Perfect. Now, in order for composition to work, there needs to be a little bit of overlapping going on so that things can flow through from the very left side to the very right side. Let's go ahead and mark this as the range of f for completion. All right, so now let's do that. So now I'm going to take this x value from the green section. Now when we do the green section, we're really looking at pieces of the composition. So in the green, and you can see I had the yellow for the g function, I had the blue for the f function, and what do you get when you put yellow and blue together? You get the green function, right? So that's the way this works. So now I'm going to take this x function and I'm going to map it with g, and that's going to lead me to g of x. But I don't stop there. I take the g of x and I continue and I map it with the f function. Well, now what do you get? Well, I didn't start with x, I started with g of x. So this must be f of g of x. So what's in this green section right here is the domain of the composition, f composed with g. We bypass the middle part and we go all the way over to the last green section here, and that becomes the range of the composition f composed with g. And really what we're looking for here is this mapping, the one that goes from x all the way over to f composed with g, f of g of x, and that's the f composed with g function. So now we can sort of figure out what has to go on here. So as far as f composed with g, you start with the domain of g. But notice that there might be some things that are in g that are not in the domain of f composed with g. And that's okay. That just means that f composed with g might have a smaller domain than g itself. And all sorts of things can go on. We'll see that on the next page. And then, as that gets mapped from left to right using f composed with g, you notice that the range of the composition might be a little bit smaller than the range of f itself. So the entire right side is the range of f, but just the green part is the range of f composed with g. The question is, how could this go wrong? What could possibly happen? And the secret to this lies right here in the middle. You need this middle piece to be both in the range of g and in the domain of f. So suppose that there was an x that you tried to map over to the range of g. So you have an x, you map it over with the range of g, no problem, but then somehow it ends up right here in the range of g, but not in the domain of f. Well, if it's not in the domain of f, you cannot continue to go further, because the f function won't work on that particular value. And that's what can go wrong. If you have a value of x, then you run the g function on it, and it does not end up in the domain of f, then really what you have to do is sort of backtrack and say, well, I couldn't have used that one in the first place, and that's how you end up with this smaller set, that's the green set, for the domain f composed with g. Let's take a look at example number 2. F of x is equal to x squared plus 3x minus 1, and g of x is equal to x plus 5. Find f composed with g and its domain. So f composed with g is going to be a function. So let's call it f composed with g of x. We know that that's going to be f of g of x. And that's going to be f of, and instead of plugging any numbers, we just plug in the expressions. So the g function was x plus 5. So we want to do f of x plus 5. That means that every place where there's an x in the f function, then we want to plug in the expression x plus 5. So the trick to doing that is every place where you see an x, don't just write x plus 5, but write down this entire set, the parentheses included. So open parenthesis, x plus 5, close parenthesis. And so we get, do it in red for you here, x plus 5 squared plus 3, and then there's another x, so that's another x plus 5, close parenthesis, minus 1. And then you need to work this out, and there's a shortcut here. So square the x, then do 2 times 5 times x to get 10x, plus 5 squared is 25. Distribute the 3x plus 15 minus 1. And then simplify that, and we get x squared plus 13x plus 39. And that is the function f composed with g. Now the question is, what's the domain of this function? So the first thing you want to look at is the domain of the function that comes first. The function that comes first is g. Remember that composition is read from right to left. The g comes first, then the f, and if there had been anything before that, then you keep adding on to that. So the first one is, what's the domain of g? Well, g is the polynomial x plus 5. Polynomials have the entire domain, all real numbers. We write that either as the big R or with interval notation, negative infinity to infinity. Then we look at the domain of f. Is there anything that f cannot take? And the answer is no. It's a polynomial. It has the full domain as well. Well, if both of these, they have the full domain, so the composition domain is going to be the full domain as well. So the domain of f composed with g is all real numbers. Let's look at a more interesting example. Example 3. Let f of x equal 1 over x plus 3 and g of x equal 5 over x minus 2. What is the domain of f composed with g? So we're just asked to find the domain, so let's skip straight to that. So the domain of g is the set of all real numbers that makes g defined. Well, here we have a fraction, and we have x minus 2 in the denominator. We know that we cannot let the denominator of a fraction be equal to 0. So if I set that equal to 0 and solve, I get 2. But 2 is a bad number. We can't use x equals 2. So there's one way that we could write this is like this. This is another method of writing sets and the domains. So it's the set of x. The vertical bar is read as such that x is not equal to 2, because I don't want x to be equal to 2. So that's the first step. Let's look at the domain of f. And in a similar token here, we have a denominator of x plus 3. By setting that equal to 0, we get x is equal to negative 3, and that's the bad number here. So this is the set x's such that x is not equal to negative 3. Now, some students jump to the conclusion right away that the domain of the composition must be that x is not equal to 2 and x is not equal to negative 3. But that's not quite it. And the reason is because of the way the circles and the sets worked on the page before. What this part means, because this is from the second function, this means that we can't have any g of x's be equal to negative 3. Because remember, the composition is going to go f of g of x. So the first set that we look at is the x's going into g. So that's just x's equal to negative 2 is bad. But now think about what values are you plugging into the f function. You're not plugging in regular x values, you're plugging in g of x values. So g of x cannot be equal to negative 3. Now we have to figure out what that actual x value would be and then exclude that. So if g of x is equal to negative 3, that means 5 over x minus 2 is equal to negative 3. And then we just solve this equation here. So I'm going to multiply over. We get 5 is equal to negative 3 times x minus 2. 5 is equal to negative 3x plus 6. So move the 6 over, we get negative 1. So negative 1 equals negative 3x. Divide both sides by negative 3 and you get x is equal to 1/3. And now 1/3 is really the bad value for x's in this case. So the domain of the composition f composed with g is the set of x's such that x is not equal to the 2 from the original calculation of g, and not negative 3, but 1/3. So the domain of f composed with g is the set of x's such that x is not equal to 2, and x is not equal to 1/3, because when you plug 1/3 into g, you get negative 3, which is then bad for the f function. The other way to write this in interval notation would be negative infinity up to 1/3, open at 1/3, union 1/3, up to 2, open at 2, union 2 to infinity. Let's take a look at example 4. Find two functions f and g so that h is a function that's equal to the composition f composed with g, where h of x is equal to x cubed plus 8x plus 7. So basically what you're looking to identify here is f as sort of an outer function and g as sort of an inner function. Well, if you look at the function that we're trying to represent as a composition, I think you can clearly see that there's an outer square root and an inner polynomial. And the polynomial is sort of the inside function here. So what we can do is we can say that h is equal to f composed with g, where g of x is the inside function, which would be x cubed plus 8x plus 7, and f of x is equal to the square root function. But now I have to represent the square root function, and how do I do that? Well, I just use the variable x to represent where the item would go. And then you can double check this. If you do f composed with g of x, you get f of g of x. So it would be f of x cubed plus 8x plus 7. But then the f function is the square root, and you plug in this polynomial in where the x is, so it would be the square root of x cubed plus 8x plus 7, which is exactly h of x. This is sort of, sometimes people call this decomposition, where you're breaking it apart, and decomposition is definitely not unique. There are many answers to this, and so we're just trying to find one that works, and it was sort of the obvious answer that we wanted.